You ever stop and think, what's actually keeping my feet on the ground? What's stopping us from just floating off into space? Well, it's this invisible force, this cosmic choreographer that directs the dance of galaxies and, yeah, pins us right here to our planet. Today, we're pulling back the curtain on that force, gravitation. All right, let's jump right in with a question that might mess with your head a little. Right now, as you're listening to this, are you pulling on the Earth, or is the Earth pulling on you? Think about it for a second. The answer? It's probably not what you'd expect. So, here's our game plan for this deep dive. First, we'll talk about the universal attraction. Then, we're going to decode the famous gravity formula. After that, you'll find out how to weigh a planet. Yes, really. We'll also look at how gravity's grip changes with altitude. And finally, we'll explore how satellites pull off their incredible balancing act up there. So, back to that question. Who's pulling on whom? Well, the amazing, mind-blowing answer is both. It's a two-way street. You are pulling on the entire planet Earth with the exact same force that it's pulling on you. It's this fundamental mutual connection that ties everything together. And this isn't just some neat trivia. It's the core of Sir Isaac Newton's incredible discovery. His law of universal gravitation basically says everybody in the universe attracts every other body with a force. It's universal. Everything with mass, you, the device you're on, the most distant star you can imagine, is locked in this constant gravitational tug of war with everything else. But, saying everything pulls on everything is one thing. How do we actually measure that? How strong is that pull? Well, Newton gave us the key, a single, surprisingly elegant formula that lets us calculate the force of gravity between any two objects, anywhere in the universe. So let's break this down. The basic idea is simple. Just take any two objects, any two things with stuff in them, like these two masses we're calling M1 and M2. According to Newton, they are always, without a doubt, pulling on each other. No exceptions. And this is it. This is the key to the cosmos we were talking about. Now, at first glance, F equals G times M1, M2 over D squared might look a little intimidating. But trust me, it's actually a beautiful piece of mathematical poetry. Let's decode it together, piece by piece. First up, we've got the F. This is pretty straightforward. It stands for the gravitational force. It's the answer we're looking for, the final number that tells us exactly how strong that pull is between our two objects. Okay, next are M1 and M2. These just represent the mass of each of our two objects. And you can think of mass as just how much stuff an object is made of. The relationship here is super simple. The more mass you have, the stronger the gravitational pull. Makes sense, right? Now for D, which is distance. And this is where things get really, really interesting. See how it's D squared in the formula? That little squared makes a huge difference. It means gravity gets weaker, and it gets weaker fast as objects move apart. This is what we call the inverse square law. Double the distance, and the force drops to just a quarter of what it was. And finally, we have the superstar of the show, G, the universal gravitational constant. This is kind of like the secret ingredient, the special number that makes the whole recipe work for the entire universe. And look at how tiny that number is. That's why you don't feel the gravitational pull from, say, your coffee mug. The mass is just too small for that tiny constant to produce a force you'd ever notice. So, okay, we've got this incredibly powerful formula. We've decoded it. Now, what can we actually do with it? Well, how about something that sounds completely impossible? Let's use it to weigh the entire planet Earth. I know what you're thinking. How on earth is that possible? How can a formula about two little masses and the distance between them tell us the weight of our whole world? There's no cosmic scale big enough, right? Well, the solution is just pure genius. It's all about a brilliant piece of logic. You see, we have two different ways to describe the exact same thing, the force of gravity pulling on an object at the Earth's surface. First, we have Newton's big universal law. But we also have a much simpler one, force equals mass times g, little g, the acceleration due to gravity. So, since they're both describing the same force, we can just set them equal to each other. We do a little bit of algebra, and boom, we can solve for the one thing we don't know, the mass of the Earth. And what do we get? We get this, 6 followed by 24 zeros, kilograms. Just take a second to let that sink in. It's a number so huge it's almost meaningless. And we figured it out, not with a giant scale, but with the pure power of an idea, captured in one equation. All right, so we've weighed the Earth. We know it has a powerful pull. But what happens to that pull as we move away from it? Let's take a look. Remember that inverse square law we talked about? Here's where it really comes to life. That acceleration of gravity, that little g, it's not some constant number. Oh no, it changes. As your altitude, your height goes up, g goes down. So if you go up in altitude equal to the Earth's radius, about 6,400 kilometers, the pull of gravity is only 1/4 as strong as it is on the surface. Go up 2 Earth radii, and it's just 1/9. It fades away fast. And this fact that gravity weakens with distance is absolutely crucial for our final topic today. How in the world do we keep satellites up in orbit? Because it's a constant, high-speed, cosmic balancing act. So how do satellites just hang up there? They don't, really. It's all about balance. On one side, you have gravity, constantly pulling the satellite straight down towards the Earth. But on the other side, you have the satellite's own motion, its inertia. It's moving so fast that it wants to fly off in a straight line into deep space. When these two forces are perfectly precisely balanced, the satellite enters a state of continuous freefall. It's always falling toward the Earth, but it's moving so fast sideways that it constantly misses. And that is what an orbit is. And the speed you need to pull off this trick, it's just mind-boggling. To stay in what we call low Earth orbit, a satellite has to be traveling at nearly 8 kilometers, not per hour, per second. That's fast enough to whip around the entire planet in about 90 minutes. It is the exact, perfect speed needed to keep falling and keep missing. You know, it all started with a simple observation, maybe an apple falling from a tree. And from that, Newton's law gave us the power to weight our own planet and command the heavens. It was the key that unlocked our entire solar system. It really makes you wonder, doesn't it? What incredible mysteries will the next great scientific key unlock?